Okay, so this is my video for standard 3.2. I chose a problem that has to do with the smallest length of a gap between two Stern Gerlach detectors that will allow a spin flip with a given probability. So they give us that the initial state of the beams is this right here. And since we know that, oh, and I guess I should mention that they give in the problem they give that the beam is traveling along the z-axis with the magnetic field along the x-axis, but I just switched it around so that the beam travels along the x-axis and the magnetic field is along the z-axis because I'm more comfortable working in the z-basis because of the previous calculations that we've done, and they are equivalent situations. So the probability that I calculate should be exactly the same. So with that in mind, our initial state is this, and then the Hamiltonian, due to the magnetic field orthogonal to the direction that the beam is traveling in, is this. So since our initial state is already written in the energy basis, we know that our time evolved state, because due to our derivation of the case where the Hamiltonian is time independent, the time evolved state is going to be this. So now we can calculate the probability of measuring spin down in the x direction, and this corresponds with the probability of having a spin flip, and that probability is just the modulus squared of the spin down x state inner product with our time evolved state. So we do this here, we find that the probability is 1/2 times 1 minus cosine of mu naught t. And this makes sense that our probability is time dependent because we are in a situation where the x and y spins are going to be precessing around the z-axis. So now we want to see how long it'll take for this probability to equal 25%, which corresponds with 50% of the spins emitted by the first detector having been split. So we set it equal to 25 and solve for t. We get t is the inverse cosine of 3/4 over w naught, and this is just a real number, and I'm leaving it in exact form just to make our final answer look a little nicer. And then therefore, since our particles are traveling at velocity v, which is given by the problem, that the smallest distance that we can expect 25% of the particles emitted through the first spin flip is that velocity times the time that we found by setting our probability equal to 25%. So therefore, the distance that we need is this. And depends on v, which is exactly what we'd expect. So as v goes up, we're going to need a larger distance for the spins to flip because they will be in the gap for less time. All right.